This is an introduction to the nomenclature of inorganic compounds. So we need to go over the difference between chemical nomenclature and common names. So chemical nomenclature is the systematic naming of chemical compounds, while common names are arbitrary names not based on chemical composition of the compound. So from chemical nomenclature, you can always tell the formula from the name, but with a common name, that's not quite doable. So let's go over some examples just so you can tell the difference. So we have salt, which is typically table salt, and this is the chemical formula for that is NaCl, and the chemical name is sodium chloride. So from sodium chloride, you can tell that the formula will be NaCl, but from salt, you can't quite tell that. Another common example that's given is a lime, which is calcium oxide, or CaO, if you're looking at the chemical formula. And again, you can tell from the name that the chemical formula, but not from the common name. So the first naming system has to do with ions. So with ions, there are two types: cations, which are positive, and anions, which are negative. So first off, cations are pretty simple. So if we grab a periodic table, here, it's pretty easy to tell which elements will form cations. Usually metals are the only elements that will form cations. So this column, all of this stuff, basically a significant majority of the periodic table. And that includes the lanthanides and the actinides. And from the position on the periodic table, you can often tell the charge of the the cation, excuse me. So, for example, if you look at row 1, which is this row right here, this row will always form a charge of +1 and +1 only. Now row 2, we'll use blue, row 2 will form a charge of +2. The row here, underneath boron, the aluminum family, will form +3, and the carbon family will form plus or -4. Now there's a significant chunk of the periodic table left out in this, which are the transition metals and the lanthanides and the actinides. These guys form multiple ions. So what do I mean by that? Well, if we look at magnesium, magnesium only forms one ion, magnesium plus, where it loses +2, where it loses 2 electrons. But if we look at iron can form 2 ions. It can form Fe +2 and Fe +3. Now, if the element only forms one ion, the name of the ion, if it's a cation, is the same as the name of the element. So this is just a magnesium ion, or magnesium. Where things get more complicated, however, is if you have 2 ions. If we have 2 ions, well, there's 2 naming systems. There is the stock, and there is the traditional. The stock system is the easiest to go with. So let's start with that. So with the stock, you simply write down the name of the metal, or, well, the element. In this case is iron. We're using iron as our example. Followed by the charge of the ion as a Roman numeral in parentheses. So iron 2 is this right here, Fe plus 2. And it's said that way, it's said iron 2. And if we're talking about Fe plus 3, it would be iron 3. Now the traditional naming system uses the old name and the suffix. So for iron 2, we're going to use its old name, and you can actually tell from the periodic table, its symbol is Fe, and its old name is ferric. So we start with we start with its old name, which is ferric, I think. And for the lower charge, you drop the ending and add an us at the end. So it would be ferrous. Now, so these two are the same thing. These two are equal. And for iron 3, since it's a higher charge, it becomes ferric. And in the case that an element doesn't have that older name, for example, titanium, you have titanium 3 and titanium 4. In the stock naming system. So since titanium doesn't have an old name, then for its traditional name, it becomes titanus and titanic. And remember, the us is always the lower charged ion. And if there's a gap in between the two ions, for example, arsenic, where it's arsenic 3 and arsenic 5, these two still apply. The old naming system still applies. The lower charged one, arsenic 3, would become arsenis, and the higher charged arsenic, which is arsenic 5, would become arsenic. Now, anions are a whole different case. They become far more complicated. Now, there's the basic anions that elements can form, which you can tell from the periodic table. So if we bring another periodic table here for anions, and we skip this over. Now, if you remember, carbon can form a plus or minus 4. And if we keep moving left, you can have plus 3. I mean, not plus 3, sorry. Minus 3 in the nitrogen family. Minus 2 in the oxygen family. Minus 1 in the halogens. And of course, the noble gases don't form ions. So we'll just ignore these. They don't matter. So to get the names, if it's just the element by itself, for example, fluorine, which if we look at the periodic table, fluorine's in this row, so it'll form a -1. So fluorine negative. Then the name just becomes fluoride. You drop the end and add an "ide" at the end. So fluoride. And this is done regardless of the charge. So oxygen, which becomes -2, is oxide. Nitrogen becomes nitride, phosphorus becomes phosphide, sulfur becomes sulfide, and so on and so forth. Now you can also have polyatomic anions. And in a polyatomic anion, the naming system becomes far more complicated. Typically, in a polyatomic anion, you will have an oxygen. In this example, we're going to use nitrogens through 4 different polyatomic anions. So we have NO, NO2, NO3, and NO4. Now, the only one you need to memorize is this one here. You need to memorize the formula for this one, because the other ones you can tell. So this one is nitrate. You need to memorize the one that has an ending of nitrate. Now, if you have one less oxygen than nitrate, the ending becomes nitrite. So it becomes an ite at the end. And if it becomes even lower, it becomes hypo, meaning low. In this case, lower oxygen becomes hyponitrite. And if, oh, by the way, all of these are -1. And if you have one more oxygen, you add a per in the front. This per is short for hyper, meaning more. So you have pernitrate. Now notice how all of these have the same charge and the same two elements. The only difference is the number of oxygen. So if you memorize the charge and the number of oxygens in nitrate, then you can get the other ones. If you forget how many oxygens there are in the 8, then it's usually going to be 3, but not always. Another example is chlorine, which is ClO minus ClO2 minus ClO3 minus and ClO4 minus. Now this becomes hypocarbonite, and ClO2, oh sorry, not carbonite, chlorite. This becomes chlorite. ClO3 becomes chlorate. And ClO4 becomes perchlorate. Now there's one more prefix that you have to learn, and that is bi. And to learn bi, we have to look at carbonate. Oh. So if we move down a bit more, we can look at carbonate. So if you see, so let's just look at carbonate by itself. There's the rest of the carbon things. There's carbonite, there's hypocarbonite, there's percarbonate, but we're only going to look at carbonate to specifically look at this. So carbonate is CO3 minus 2, and this is carbonate. Now, if we add a bi in front, in the case of bicarbonate, this means that we're adding a hydrogen in front. So this becomes HClCO3. And whenever you add a hydrogen, the charge gets higher by 1. So it goes from -2 to -1. So this becomes bicarbonate, which is HCO3 minus. And this also happens for sulfur. So you have sulfate and bisulfate. So sulfate is SO4 minus 2, and bisulfate is HSO4 minus. And sulfate is one of those cases where the 8 is actually SO4. So you can see this is SO4 minus 2 is sulfate. The other terms still work. So sulfite is SO3 minus 2. This is sulfite. So you can see we just removed one oxygen. And persulfite, you just add another oxygen. So SO5 minus 2. And this is persulfite. So that's about it for ions. So next we should move on to binary ionic compounds. So binary ionic compounds are pretty simple as well. So a binary ionic compound is essentially something, for example, potassium bromide, which is KBr. But there are a few special rules. So first, going from the formula to the name is really easy. If you have this, you just take the name of the first ion. So this is K+, and bromium forms a -1 ion. So the name of the first ion, remember, in a cation, it's just the same as the element. So this is potassium. And then the second element is bromium, but it has a charge. So remember, a cation that is formed by itself, it changes its end to an ide. So this is potassium bromide. Now, there's a few other examples. For example, Li2S. So this is lithium. And this is sulfur, but since it's from an ion, it becomes sulfide. And remember, in ionic compounds, we ignore the coefficients here. Not the coefficient, the number of elements that there are. So this little subscript number here, we ignore it. Now, going from the name back to the actual formula is a little bit more tricky. So let's take calcium phosphide. Calcium phosphide. If you have calcium phosphide, well, you know you're going to have calcium, and you know you're going to have phosphide. So that's a P. And remember from the periodic table, we know that phosphorus forms a -3, and we know that calcium forms a +2. Now what's going to happen is this +2 is going to go down there, and this -3 is going to go down here, but they're going to lose the plus and the minus in front. So the final formula is Ca3P2. And the reason we do this is because we want the final element to have a neutral charge. So if you have 3 calcium, that means since each calcium has a charge of +2, if all the calciums together will have a charge of +6. Now, if you have 2 phosphides, each phosphide will have a charge of -3. So together they'll have a charge of -6, and these two will cancel out. So you'll have a charge of 0 for the entire binary ionic compound. Now, there's one more case that we have to cover. So, for example, let's take magnesium oxide. Magnesium oxide. If we have magnesium oxide, then we know that we're going to have magnesium and we're going to have oxygen. Magnesium forms a +2. Oxygen forms a -2. So if we move this here, and we move this here, then we're going to get Mg2O2. But with an ionic compound, we want to simplify this. So it's like in math, you can factor out the 2, and they will both cancel, and you will get MgO. And these will still cancel because Mg will have a charge of positive 2, and oxygen will have a charge of negative 2, and they'll cancel out. Now, that's it for binary ionic compounds. So if we move on to tertiary ionic compounds, this is formed between a cation and a polyatomic anion, or a polyatomic cation and a anion. So, for example, we can have potassium nitrite. So if we remember, potassium forms a charge of +1. So this is K and +1. And then we have our NO3. And this forms a charge of -1. So then this will go here, and that will go there. And eventually you'll just get KNO3. Now, it does get a little bit harder when they have different charges. So, for example, if we have calcium nitrate instead, and you can see we have the I and the 8 from the polyatomic anions and their naming system. Calcium nitrate. And if we look at this, so, we have calcium, and we have nitrate, which is NO3. Oh, sorry, this is an NO2. I don't know why I wrote 3. This is NO2. Nitrate is NO2. If we have nitrate, we have NO3, which is minus, and calcium forms a +2. So then the 2 goes to the end here, and the minus goes here. But we can't have a subscript, and we also can't we can't move the 2 to the, so it becomes N2O6, because then it doesn't form a polyatomic ion anymore. So what we do is we put it in parentheses. So we have Ca, and the -1 we don't include it because it's always assumed that it's 1. And then the NO3 we put in parentheses, and we move the 2 outside. So that's the charge from the calcium outside here. And going backwards is also really simple. If we take AlNO3, oh, sorry, this is supposed to be in parentheses, NO3, and this has 3 of these, then we know this is aluminum, and the polyatomic ion of aluminum just stays that way. It's just aluminum. Aluminum. Or if you're not from the US, aluminium. And then the NO3 is nitrate, so we just add the nitrate at the end. And then we also have a case where you can have the polyatomic ion be the cation. So this is, for example, NH4 and S. So this is ammonia right here. So this becomes ammonium and sulfide, because this is a anion by itself. So ammonium sulfide. And then we get to the tricky part, which is where you have binary or tertiary ionic compounds with what are called type 2 cations, which is with those elements that can form multiple cation. So for example, iron or copper. So all you do in this case is the actual written name changes, and each of these have two names. So if we take FeCl3, we can figure out what the charge was, because remember this 3 here means that 3 goes there and the 1 goes here. So this means this was iron plus 3. So this is Fe plus 3 and Cl minus. And so we make two names, one with the stock and one with the traditional naming system. So remember, with the stock naming system, we use the name of the element and then its charge in Roman numerals. So that's a 3. And then chloride. And then it works the other way as well. So remember, iron 3 is the higher cation that iron forms. So this is ferric. Ferric and then chloride. And all of these work the same way. And these two are the same name for this one element. So now you can have copper, and in this case, oxygen has a charge -2, and the 1 goes from here to the copper. So this is Cu minus and Cu plus and O minus 2, because the 2 from here goes up there. And that means this is copper 1. So this becomes copper 1 chloride. Or cuprous chloride. And that's all there is to ionic compounds. So now it's time to talk about binary molecular compounds. So first off, we need to look at the ending, which ends in this suffix "-ide". This is the ending for the entire compound, not every element in the compound. Now, for every element, to indicate the number of elements, we use these prefixes. For 1, it's mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca, 11 is undec, 12 is dodec. Now you'll notice that most of these are the same as the prefix for shape, or another common thing, except for di, tetra, mono, and I believe undec and dodec, but I'm not sure about these two. Now, the only exception to this, being used everywhere, is mono. Mono is not used for the first element in a compound. So for example, if we take carbon monoxide, CO, you'll notice I said carbon monoxide, not monocarbon monoxide. And this only works for the first element, and only if there's one of it. So if you take a different compound that has a different number of if you have an element that has, for example, 2 of that element as the first element, then you would say di and then the name of that element. Now, another example is Ci2. So once again, we don't add a mono in front. This is carbon. And since there's 2 iodides, it becomes diiodide. And then for carbon dioxide, we all know this. This is CO2. And this becomes the carbon from the start. And since it's the very first one, we don't add a mono in front. And this becomes dioxide. Now if we take glucose, which is C6H12O6, this would become hexacarbon dodecahydrogen. Hexaoxide. So you can see these chemical names can get very long. Except for one minor problem. This name is completely wrong. Why? Well, this system is for naming inorganic molecular compounds. Glucose is an organic molecular compound. So this system wouldn't work at all for it. It has its own organic compounds have their own way of naming things. That won't be covered in this video. So we're just going to erase this. Of course, going from naming to actual formula is also really easy in this version of this way of naming things. So carbon tetrachloride, for example, so since there's no prefix in front of the carbon, we know there's only one. And tetra means 4, and chloride means chlorine, so Cl5. So in order to use the system, you really need to know all of these prefixes. Now there's just one more thing that we need to learn how to name. And those are maybe the most complicated of them all. And they're acids. Now, if you'll remember, acids are from ionic compounds dissolving in water. So they will always have two names. One is their so-called dry name, which is when they're not an acid, and then they have their acid name. So the dry name is just the name of the compound as an ionic compound. So for example, if you have HCl, well, its dry name, we can remember this is hydrogen, so it'll form a +1, and chlorine will form a minus. So this just becomes HCl, and we take the hydrogen and since this is a cation, it's just the same name. And then the anion, this is by itself, so it changes its ending to an "ide", so it's chloride. So hydrogen chloride. And it's pretty simple for the dry name. Now the acid name is where all sorts of fun happens. Now to represent that this is in acid form, we write AQ in parentheses here, which means aqueous or dissolved in water. Now, if this is a simple binary ionic compound, like hydrogen chloride was, HCl, then what happens, this is called a binary acid, since it's a binary ionic compound, and what happens is you change this hydrogen to a hydro, becomes hydro, and the Cl changes its ending, the chloride changes its end to an ic, so it becomes chloric. So hydrochloric acid. This is a very common acid. In fact, it's inside your stomach right now. Now, there are obviously a few others like this, but this naming system is pretty simple. Now, you have another thing known as oxyacids. And this is where you have hydrogen bonded to a polyatomic cation that has oxygen in it. So, for example, if you have H2SO2, this should be an oxyacid because you have an oxygen hanging out with the rest of this. Now, in this case, what happens is you just ignore the hydrogen. This doesn't show up in the name. You don't get like a hydro in front. And then the SO2, well, this is sulfite. Well, this is hyposulfite. So the ending changes to an us if it ends in ite. So this becomes, well, this is sulfite. Well, hyposulfite, sorry. Hyposulfite. So we remove the ite and change it to an us. So hyposulfurous acid. Well, what if it ends in an 8? Well, if it changes in 8, so this would be H2SO4, this is hydrogen sulfate, then you would get sulfuric acid. So 8 becomes ic, and ite becomes us. And these are the naming rules for oxyacids. Remember, if it doesn't have an oxygen just hanging around, then it's a binary acid, and you just add a hydro and then change the ending to an ic, so hydrochloric acid. And remember, prefixes stay. So for example, if it's hyposulfite, then it becomes hyposulfurous acid. The prefix will stay. But with acids, you never add a prefix if it's an oxyacid. You only add them if it's a binary acid. So going back from acid to the formula, for example, if you have nitrous acid, well, we know that nitrous is nitrite, so that's NO2, and we know this is bonded to some sort of hydrogen. And since hydrogen forms a negative, a positive, and NO2 is a negative, these two will go to the opposite sides, and it becomes HNO2 aqueous. Never forget the AQ at the end if it's acid form. And the dry name for this would be hydrogen nitrite. So that's it for naming acids, and most of the inorganic compounds.